This video is on the class question slides for resistivity and power. The way I recommend using this video is each time I flip to a new question, pause the video, read the question, answer the question in your own mind. Ideally, hopefully you're watching this with a classmate or group of classmates. After everybody's arrived at their own answer, discuss it as a group, arrive at a group answer, and then unpause the video and see what I have to say about it. So with this first question, we've got electrical energy converted into thermal energy at the rate of 5 watts. What's the power? They want to know. And power, by definition, is the rate at which energy is transferred or the rate at which energy is converted. So they say the rate at which energy is converted is 5 watts. So by definition, the 5 watts is the power. And that would be answer C. Okay, next question. This time it's the same situation, but they want to know how much energy is converted into thermal energy. Now, the power is the rate at which energy is converted. In this case, that's how many joules per second of energy is being converted into thermal energy in the resistor. Well, that's going to be the power is thus 5 joules per second, and it's a constant value of power. So in order to get the total energy, all we have to do is multiply the energy per time, namely the power, times the time. So that's going to be 5 joules per second times 1 minute, which is 60 seconds. 5 times 60 is 300. It's joules per second times seconds, works out to be joules, so we got 300 joules. Answer B is the correct answer for this one. Now, we've got 2 wires, but both made of the same kind of metal, and they want to know how the resistivities compare. Well, the resistivity is a property of the material. They state that the materials are the same, so the resistivity has to be the same. So the size and shape of the wire doesn't matter, as long as you have a good handle on what we mean by resistivity. No, it's not a trick question. It's obvious that the resistivity of wire B has to be the same as that of A. So that would be answer A for this one. Now we got 2 wires, same length, same material. B is twice the diameter of A. How does the resistance of B compare with that of A? B's fatter, so it's like it has a larger avenue for the charge to flow through. So the resistance of B is going to be less than that of A. They want more detail. They're asking twice or 4 times. So let's take a quick look at the formula sheet. We've got over here the resistance is rho times L over A. That's the resistivity times the length divided by the area for the wire. I'm going to go ahead and write that down. The resistance, what we're asked to compare, is equal to the resistivity times the length divided by the area. Now, for the 2 wires, the length and the resistivity are the same. It's the diameter that's different, and the diameter is related to the area. Now, first, the area is pi r squared, where r is the radius, but r itself is the diameter divided by 2 squared, so we've got the area is proportional to the square of the diameter. The constant proportionality is pi over 4, but that's not the part that matters. So for the fat wire, as compared to the skinny wire, downstairs we've got twice the diameter, which means 4 times the area. So we'll have an extra factor of 4 as compared to the skinny wire in the denominator. So that makes the whole side 1/4 what it would be for the skinny wire. So the resistance of the fat wire is 1/4 the resistance of the skinny wire. It's B is the fat wire. Resistance of B is the same. Twice, 4 times. None of those answers are in there. I guess I could have picked up on that without going through it all if I had read all the answers, because I mentioned right off the bat the resistance of B is smaller than that of A, and I noticed that they were getting more detailed than just smaller, but all they've got is the same or bigger as the possible answer, so even without going through the math, it would have to be D, none of the above. Now we got 2 wires, same kind of metal, same diameter, but B is twice the length of A. So I can look at the formula we just had written down. The longer it is, the greater the resistance. So they want to know why is the resistance of B less than the wire A, but B is the longer one. B having twice the length of wire A. B is the long one, so B's got the greater resistance. So it's not. The premise is wrong. Okay, it isn't, is one of the choices. Looks like A's got to be it. Yeah, A is the answer to this question. Okay, let's move on to the next one. Okay, same situation as before, but this time they're asking the more sensible question. Why is the resistance of wire B greater than that of A? Farther to go. Alright, let's get a little bit of a drawing. We put a piece of wire, make it look kind of fat so I can draw inside it. And we'll create a potential difference between the ends of it, a voltage V. And if from V is equal to IR, R is V over I. And what we're saying is if the resistance is bigger, that means we're going to have a smaller current for the same V. And the question is, why might we have a smaller current for the same V? And I want to look at the electric field to see if that could have anything to do with it. Our electric field is related to the potential. I worked this out in class one time. It goes the X component of the electric field, and I'll call X being that away, plus X is to the right, is minus dV by dx. So we do have an electric field in this wire. It's not a perfect conductor. If it were a perfect conductor, it would have 0 resistance, and we're talking about the resistance of it. Furthermore, it would have no electric field in it, but it's not a perfect conductor. It's it gets some resistance. So in the case of a constant, or uniform really, I'll go ahead and write it down as uniform. This just becomes, oh, this was d phi by dx. Sorry about that, d phi by dx. So delta phi divided by delta x, which is the voltage that we were talking about, the potential difference between the ends, delta phi, phi high minus phi low, is V by definition, and we call this the length of the whole thing. So we got this electric field in here, extends from high to low, and for a given V, for the same V, for instance, for different length wires, there's an L in the denominator of the expression for E, so the bigger L is, the smaller the electric field, and hence the smaller the charge flow rate inside the material. So the deal is, you make the wire longer, You're going to make it so that the electric field inside is weaker, and that means the terminal velocity of the charges flowing through there is going to be smaller, and hence that corresponds to greater resistance. You get a smaller flow rate, which small flow rate corresponds to big resistance, just by common sense or by this formula, whichever way you want to look at it. So what do we got? Why is the resistance of wire B greater? It's because B has a smaller electric field. Let's see if we got that one. There we go. Because the electric field is weaker in wire B. Answer C. And then we're moving on to another topic. So that does it for this video on electric power and resistivity.